if I can remember, did we look at this example? Which one? Let me look. This one. Where is the problem? Okay. Did we? I think we stopped somewhere here. Right. Last week. Let me check. Yeah. I think we didn't discuss about this example. All right. So we are going to discuss this in detail. Actually, the similar explanation can be found in my recorded video in the YouTube. I don't know whether you have watched that video or not, but actually, if you already watched that video, it is actually very helpful because you can repeat watching that video as you like. The explanation that we are going to discuss tonight actually very similar to what we have in the YouTube, which is I think we may go or look at this problem quickly, and then we can move into another problems on the plane trusses. All right. Okay. In this, if you still can remember, in the theoretical part of the plane trusses, says that our plane trusses can be viewed in local coordinate systems, where when we view our structures in local coordinate system, then our structure will behave very similar to the 1D bar problems as we seen in the previous topic. But the plane truss structure is not a single piece structure or single element structure. It's combinations of several slender members that is connected at rigid connections or points, and where all the loads will be applied at that joints. If we still can remember the definitions of the plane trusses before, right? And so in this example, this is maybe the small part of the plane trusses that we take out from maybe very big structure. We have, this is maybe came from very small part from the, if we still can remember, we have example of this, for example, this complex truss structure to make what we call it, the bridge, right? So our structure just now may came from maybe one triangle and the other one joins only from out of maybe thousands of plane trusses that we can see in this bridge. And all right, where is it? Okay. So the purpose of this example, which is to show you how we can how we can deal with these plane trusses or part of the plane trusses using finite elements, which is if you are going out to work in the future, you may solve maybe more than 4 elements that we have in this example. Maybe you have to solve 10, hundreds elements, depend on your on the project that you handle. So the problem here is says for a plane truss shown. So we have the plane truss shown. This is our plane truss. determine the displacement at node 2 and 3. So I'm sorry, maybe my handwriting tonight is not good enough because I forgot to bring back home the writing pad. So I have to use my mouse tonight. So displacement at node 2 and node 3. So where is the node 2? Node 2, which is located here. This is our node 2. And then at node 3. Where at these two nodes, as we can see, um, this node 2 is supported by a pin roller type of support. And then at nodes number 3, it's a free end of our structures. Nodes number 1 and node number 4, it is supported by a pin fixed type of boundary conditions or support. So we have discussed about this support and how it behaved before, right? So we in this example, we would like to determine displacement at node 2 and 3, and B, determine stresses in each element. So in this example, it will show you how to determine stresses in each element. But if, for example, we just solve for one element, actually the process to determine the stress actually the same. If for example, I would like to determine the stress for the element number 1 or number 2 or number 3, the process actually is the same. It's just the elements and the geometry that differs or different between each other. And then C, reaction force at the support. So this is our support, this is our support, and this is our support. So we may have the reaction force both in X and Y at point 1 and 4. And then we may have reaction force in the Y direction at nodes number 2. And given that the material used that have this modulus of elasticity as shown here. So 29.5 times 10 to 6 to 10 power of 6 pound per square inch. So to it's good to highlight here as well. This we use the imperial units only for example here because we take it directly from the textbook. But for the purpose of the test and exam, we will use the SI unit. All right. And given the area of each element, so A here is actually the cross-sectional area of our element, which is given by 1 inch square for all elements. All right, now the first step, we know that for every element, we have to come out with these the element stiffness metric for each element. So given that now our um, K matrix, which is having this 4 by 4 in terms of its size. But in this lecture notes, the way it's solved, the solution provided in this lecture note actually shows the step-by-step solutions to the problem that we would like to determine. But the solutions or the approach that we have in the slide here, if you follow it as what we have in the slide, then it will take I think a longer time for you to solve the problem. So in order to minimize the calculation time, because during the test and exam, often students are struggling with the time rather than the theory or understanding of the problem. So in order to minimize the time, so I suggest all of you, once you have these problems, um, then straight away look at the boundary condition. So when we look at this boundary condition, we can, if we know which boundary condition is active and inactive, we can minimize our process in preparing the element stiffness metric, especially. So if we look at these problems, so in your test letter or exam, once you have the geometry something like this, for plane trusses problem, for example, then straight away draw the degrees of freedom at each node point, like what you have on your screen now. Then from there, look at the boundary condition. What is the type of boundary condition that we have at point number 1? So we have pin fixed, which is for the plane trusses, we don't care about the rotations of, at the joint, because we just care about the displacement in the x and y direction. So the pin here actually means nothing actually, the pin, because pin often we use for rotation to display the flexibility of our system to rotate. But for the plane trusses, we don't care about this rotation. So in this case, at point number 1, it is resembles that this point here, like we or a support at this point 1 here is resemble that this point is under the fixed support. That means there will be no displacement at all at this point 1, both in x direction and also in the y direction. So just straight away put it something like this in your exam or test paper. So number 4, we have similar boundary condition. Then straight away the displacement will be equal to 0 in both x and y. For point number 2, then what we have here, we have roller oriented in this direction. So we expect that at point number 2, this point number 2 have the flexibility to move to the left and to the right, but there will be no displacement in the vertical direction due to the fixed support here. So for the Q3, we may have displacement later. At nodes number 3 here, we have 2 degrees of freedom as well. So this particular this point is freely to move in both direction x and y, because there is no support applied at nodes number 3. So under the given load 25 pound pointing at nodes number 3 in the downward direction, and 20,000 pound applied at nodes number 2 in the x direction. So under this two load, then we expect there will be changes in the locations of nodes number 2 and nodes number 3 after the load applied to the structure. So when we have this, then we can start develop the so this is what we are going to prepare later. KQ equal to F we understand that we have 4 elements. So out of this big K, it must be actually came from the assembly of K1 plus K2 plus K3 and K4. But it is not a element by elements addition, but it's more to the address, what we call it as the ing, the correct address in term of ing. So later we will look at on this. All right. So for each element here, for element number 1, we expect to develop K1. We will have a K2. We will have K3 later, and then we will have K4. But what is our K? So this is our K. Our K metric depends on the L and M, which is L refer to the cos of the angle of our element, theta, and then M, which is the sine of the angle of our element, theta. Okay, now we know that this is the K, our K metric, and then how it looks like. And then what next is to evaluate the angle of our element according to the element connectivity. So this is our structure. Okay, so we have similar structure here, and given the nodal coordinate, so when we have a structure, we can give the origin to our structure. In this case, this is our origin for the x and y at nodes number 1. So I will have x0 and y0 at x at nodes number 1, and then the length of my element number 1, which is 40 inch, the length of the structure in the vertical direction, which is 30 inch. All right. Before this, when we discuss about 1D bar problem, we have to develop the element connectivity table, but our element is connected point element by element. It has a continuity connection between element. But in this case, there is no continuity connection between the element. For example, element number 1 here is not directly connected to element number 4, right? So they are separated. There is no direct connection between node 1, node 2, and node 3 and number 4. But it is connected to element number 2 first and number 3 before it can connected to element number 4. For this kind of problems, then this element connectivity becomes very important. Why? Because this element connectivity will determine your angle theta. So when you have these structures, sometimes we provide you element connectivity, and in some cases you have to decide how to build this element connectivity for your structure. Okay, now let's look how we read this element connectivity. So for the element number 1, so this is our element number 1. it says that this element is connected from nodes 1 to nodes 2. So in my case, I like to draw the direction of the element connectivity for the nodes number 1. So it connected from 1 to 2. All right, for the element number 2, it is connected from from 3 to 2. Okay, instead of it's connected from 2 to 3. But we decided, okay, for this particular element, it is connected in that way from 3 to 2. For the element number 3, okay, it's connected from 1 to 3. So from this point to this point. So I draw it, the directions of the connectivity. And the same for the element number 4. All right. Now, if all right, now um, if we look first to the element number 1, okay, and then we take our reference axis. Our reference axis is the horizontal axis. All right, this is our reference axis at nodes number 1. So our element here is actually moving from 1 to 2. So from 1 to 2, and then the angle here, we can say that the angle from 1 to 2 here is equal to 0, 0 degrees. Because it's moving in this line, right? And then let's we look at the second element. Maybe you're still confused. Is it 0? Is it 90 degrees? Or is it 360 degrees, right? So let's we look at this element number 2. Our structures here, our elements number 2, okay, it is connected from 3 to 2. So we take at node number 3, we make the horizontal line to represent our reference axis. All right, from 3 to 2, it is moving from here. It moving from this axis, then until it reach the element number 2. So how much the angle here is 270, right? 270. Okay. Next, we look at this element number 3, which is it is connected from 1 to 3. So we have this reference axis. Then we project from the reference axis until we meet the this element. So in this case, we have to calculate a bit lah, from the trigonometry. So we have we have the sine of 30 over 40. So if we take sine, the sine inverse of 30 over 40, then we will get the angle theta here. So we will calculate it later here. For the element number 4, okay, this is very similar to number 1. So this actually 360 or 0 actually will give you the same angles, right? If we take the cos and sine. Okay, so for the element number 4, then our nodes here is moving from 4 to 3. So along this one, along this line here, then our angle also will equal to 0. But let's say I take one example. Let's say we change the angle of the element connectivity for the nodes number 4, which is it is connected from 3 to 4. That means it is connected from 3 to 4. So what is our angle for this element number 4? So since node 1 is started at 3, so we make reference axis at nodes number 3. Then this element is connected from 3 to 4. And we make the measurements starting from this reference axis until it meets our element number 4. So in this case, if the connectivity of our elements is reverse from 3 to 4, then our angle will be equal to 90. Equal to 90 degree. And what should we do with all this angle? Okay, this angle will be used in your K metric, which is L equal to cos theta, M equal to sine theta. So you can make a list something like this. You can have, this is the length of the elements. So you can have L. Usually I like to put the angle theta here. And then L equal to cos theta. We have M equal to sine theta. And then we can have, I think I make it something like this. I have L, and I like to put L square there. And then I have M. Then I can have M square. Then I can have L multiplied by M. So in my case, I like to make a complete table, something like this, so that when I have all the value filled in this table, then I can easily use the information to prepare my element stiffness metric. So if we go to this K matrix here, all right. So I suggest you to come up with this kind of table so that it will be easy for you to plug in the numbers there. All right, next, let's we look at the element number 1. Okay, so in this slide, the way this slide is prepared for you, we feel we show everything. We show everything in terms of the number. But in some cases, you do not need to solve everything. So, for example, let's say I use this two slide here. Then I remove this, sorry. So when we prepare the element stiffness metric, as you can remember, we have to write the address, right? Like an address on the top and at the side of our matrix. So to write this, it is actually we need to refer to the element connectivity. Okay, if I can make it slightly smaller so that I can make use all of this information. So now this is our problems, the structure with the boundary condition, and then this is our element connectivity. let's say I would like to prepare the K metric, but I don't want to prepare everything. It's wasting my time because some of the metric I'm not going to use it at all. Okay. This is the metric that we are going to fill up later, but we first need to look at the element connectivity. For element number 1, our element is connected from 1 to 2. So what do we have at nodes 1 and node 2 in terms of the displacement? All right, let's we look at this one at the bottom, figures at the bottom here. Okay, at nodes number 1, so we start with the 1 to 2. So the way we write the address on the top and or index at the top and at the side of our metric is by following the orders of element connectivity. From 1 to 2, then we write the index of our displacement 1, 2, then followed by 3 and 4. So for my metric K1, let's say for K1, I can write 1, 2, 3, 4. Here 1, 2, 3, and 4 as well, which is to follow the order of the element connectivity from 1 to 2. What will be happen if my element connectivity is connected on the other way around? Okay, let's say the element connectivity now is connected from 2 to 1 for the element number 1, right? So so I draw it something like this. Then in this case, we have to start write our index around our K metric to start with the Q3, Q4, Q1, and Q2. So if our element connectivity for the element number 1 connected from 2 to 1, then we use the index of our displacement starting from nodes number 2 and in the x direction first. So in this case, I should write 3, 4, 1, 2, 3, 4, 1 and 1, 2. Sorry for my bad handwriting because I have to use my mouse uh, to put a comment on the slide. So you have to be careful with this address or indexes used in your all of your K metrics. So now, so this is just example. So we go back to the original setting of our problems. So for the element number 1, then I will write here, okay, 1, 2, 3, 4, 1, 2, 3, and 4. So you can actually prepare this before you plug in the numbers in your metric. So now you have your index prepared around your K metric. Then look at the boundary condition. So we have Q1 equal to 0, Q2 equal to 0 due to the fit boundary condition, and Q4 equal to 0 as well due to this kind of support that we use. So in this case, we can straight away eliminate 1, 2, and 4 from our K matrix. Sorry. We eliminate the row and column. So what left? So this is only what left in our K1. So instead of we write everything here, which is will take some time for you to write 100, 101. So instead of writing everything, you can reduce your work just by showing something like this. For element number 1, you eliminate all the rows and columns um, for the uh, for the index 1, 2, and 4. Then just provide the value for the element number 3. Just provide the value for the element number 3. So actually, you do not need to write everything. So if you prepare your works in that way, what left later is you can write that your K1, which is only contain, assuming we have all of this here. So this is equivalent. And then you have what is L square for element number 1? 1 square equal to 1. But you have to fill up here first. You have 1, 0, 0.64, 64, and then 1. And the same for the M, 0, 1, 0.36, and 0. L multiplied by M, 0, 0 multiplied by negative 1, 0, 0.8 multiplied by 0.6, you calculate it here. 1 multiplied by 0, you have 0. So for our case, since we eliminate all the rows and column 1, 2, 3, and 4, so instead of we write everything, so you can write something like this. But you have to write everything, the constant here, there. So if you have something like this, we can accept your answer as well. Instead of you waste your time writing the information that we are not going to use at all. So what will be happen to the element number 2 then? What will be happen to the element number 2? So let's make it smaller a bit. How should we write our index here, and which element in our matrix that should we eliminate? Can anyone of you suggest? Kita dah pergi makan nasi dah.
Apa soalan sir?
How should we prepare our K2? Yang macam yang kita buat untuk K1 tadi.
One, two, five, six.
1, 2, 5, 6.
5, 6. Yeah.
Untuk elemen number 2. This is our element number 2. It is connected from 3 to 2.
Sorry. 5, 6, and 3, 4.
Yes, betul. So we should write 5, 6, 3 and 4. Tu betul lah tu. 5, 6, 3 and 4. So when we have this, we straight away look at the boundary condition. So boundary condition untuk kita punya element number 2, which one is inactive? So yang ni 5 active, 6 active, which is we may have deformation in both direction at next number 3. Yang tak aktif hanyalah Q4 kan. Then we eliminate the row and column for the element number 4 for our K2. So in that case, you just fill up the number for all the active element in your K matrix untuk element number 2. So you reduce a bit your time instead of fill up everything in the K matrix. So untuk your K2, suppose your K2 we don't need this information. So kalau kamu tulis yang this 3x3 pun dah kita dah terima untuk tujuan test lah kan. And then you have to repeat this for all element, for the other element as well. Untuk okay, kita ada 5, 6, 3, 4. So dekat sini kita ada 5, 6, 3, 4. Untuk yang dekat sini tadi kita ada 1, 2, 3, 4.
Ini kacau.
1, 2, 3, 4 ke?
Asal lagi fokus lah. Teruk betul. Kacau.
Lepas tu untuk elemen number 3. Untuk elemen number 3, what happened to our element number 3? Okay, in terms of the K matrix. Sorry. Our element number 3 is connected from 1 to 3. So for the element number 3, from 1 to 3, kita ada 1, 2, 5 and 6. Kita boleh tulis 1, 2, 5 and 6. Sini pun sama lah, 1, 2, 5 and 6. Then we go straight away to the boundary condition. 1, 2 can be eliminated. And then 5, 6, we need this information in order to determine the displacement at this points. So we have 1, 2, 5, 6. So kalau kita diisi dengan the values dia, then kita punya matrix dekat sini nanti, we can eliminate this. You don't need to write it at all actually. You just prepare this small matrix only, which is in this case kita ada 1, 2, 5, 6. So you just prepare for 5 and 6 only. 5 and 6 instead of sebab nak tulis ni banyak ni 0.64, 0.48. So by the time kamu dah siap ni dah habis dekat kalau tulis laju pun dekat seminit juga tu. Itu kalau tak ada salah tulis. Ada salah tulis nanti masuk kita assemble dekat for the global matrix. Nanti kamu check dia dah tak simetri kan. Tu lagi satu hal. Next, kita prepare untuk K4. Kita punya K4 is connected from 4 to 3. Ni pun sama. Kita tulis dekat sini from 4 to 3. Then our index dekat atas ni akan jadi 7, 8, 5, 6. 7, 8, 5, 6. For this kind of for this element under this support or fit support, kita boleh eliminate the elements in our matrix for the elements 7 and 8. So kita tak perlu tulis the whole prepare the whole elements. So we just need only this small matrix only, which is kita punya index dia still 5 and 6, 5 and 6. So now we have something like this. We have prepared our what we call it reduced matrix. Instead of kita prepare semua ni, kita just prepare a reduced matrix. Maksudnya matrix yang kita dah simplify. Sepatutnya the whole problem ni kita ada 1, 2, 3, 4 empat nodes. Satu node ada 2 degrees of freedom. Kalau kita prepare dia, kita akan ada 8 kali 8 of the matrix. So kalau kamu nak isi semua ni, which is will take some time for you. But if we solve the way as we discussed just now, kita boleh instead of kita write everything, so kita boleh tahu dah dekat sini which element dia yang aktif. Kita tengok kat sini, elemen yang aktif hanyalah 3, 5 dengan 6 saja kan. So 3 ada kat sini, 3 ada kat sini yang aktif. Yang lain-lain adalah 5 dan 6. Cuma you have to be careful lah, you have to be careful with your constant dekat luar ni. So kalau tengok kat sini dia punya denominator yang ni over 30, yang ni over 50, this one over 40, this one over 40. So you have to be careful. The constant value should be the same kalau kita nak pakai dia, kalau kita nak tambah dia apple to apple lah kan. Otherwise you have to modify it, kamu punya constant dekat luar ni supaya semua yang ada dekat luar ni sama. So in this case, how we make it the constants equal? So we adjust so that the denominator dia adalah 600. Then bila kita ubah denominator to 600, then kita can expect the numbers dalam ni akan berubah lah. So I'm not going to show detail how we did this, but I expect you to try it yourself. How can you make from 40 to become 600? So in this case, okay, let's say kita dah convert everything dekat dalam in our constant region dekat sini ni, constant value ni to 600. Then instead of kita prepare our matrix of the size 8 by 8, 4, 5, 6, 7, 8. So kat sini pun sama lah, 1 from 8, from 1 up to 8. So instead of kita buat semua ni, then actually we can simply write our matrix K. We use a capital K to show the example element sequence matrix, or you can simply put a G to refer it to the global matrix. Then you can have the constant value there, and then only the element 3, 5, and 8. So 3, 5, and 8. Here 3, 5, and 8. How we prepare this? Very similar to we prepare the global matrix in when we solve the 1D bar problem. We have to look at the address here, then we add address by address here. For example, for the nodes, for the element 5, we have 5, 6, 3, and 4. So this 5 here will be added to this 5 here, and then will be added to 5 there, and then we have to add if we have 5 somewhere else. So okay, we don't have 5 in K1. So, but in this case, you cannot simply add 0 plus 0.64 and 0 because we have to make the denominator denominator the same for all value of k. So if we solve this approach, then you just need to prepare a 3 by 3 matrix only instead of 8 by 8 here. So this one is 8 by 8. So this process actually will reduce a lot of your time in preparing the global matrix. And in some cases, we may give you more than 4 elements. We may have 5 elements, but if you solve the problem similar to what you have, if you follow strictly the approach that supplied to you in the lecture note, then you have to prepare 10 by 10 matrix. You can imagine to prepare 10 by 10 matrix. It will consume so much of your time. Then finally, kamu tak sempat nak siap pun jawab soalan final element kan. So don't follow the lecture notes strictly lah kan. So try to consider the approach that we discussed just now. Kita ada K matrix, kita tahu boundary condition, then eliminate yang mana inactive boundary condition, which is yang displacement dia adalah kosong, straightly eliminate, and then prepare apa yang kita nak pakai dia. Tapi sekiranya soalan memerlukan kamu untuk menyediakan global stiffness matrix full global system of linear equation kan, then you have to prepare the 8 by 8 matrix. Kalau dia just cakap je prepare system of linear equation macam tu je, then you can choose both. Nak prepare, kalau rajin rasa macam sempat nak prepare 8 kali 8, then up to you. If you want to prepare only the active for the active element, then just prepare 3 by 3. So kita accept it. And in some cases soalan tu memang dia specifically explicitly mentions yang kita minta kamu sediakan hanya reduce system of linear equation. So just give us the simplified one, which is yang ni lah, yang the simplified one ni. This one ni kita panggil full system of linear equation lah kalau kita dah ada macam ni nanti. So now we have K, which is in the form of a reduced matrix, K matrix. Then we have to write this in the form of a system of linear equation kan. So our system of linear equation will be written as this KQ equal to F. So you will see this equation until the end of the semester. Alright, we have done K just now. Q is just our unknowns. So kita list everything, Q1 until Q8. But in our case, tadi tu kita dah tak perlu nak tulis dia semua. We have our K, and this is our K matrix. So our Q is just Q3, Q5, and Q6 saja. Kenapa yang ni? Okay, because this is only the active degrees of freedom. Kan? Yang ni kita nak cari. 3, 5 and 6. Yang lain semua fixed to the floor, to the wall. So kita tak perlu kisahkan dia lagi. In fact, kita dah eliminate dia punya elemen tadi kan. And then we have to look at the force. Okay, force. So what kind of force applied to our system and where it applied? So in the lecture notes, so dia prepare everything. F1, F2, F3, F4, 5, 6, 7, 8. So kalau tak ada force applied at that particular note, then we give zero radius lah kepada external force. And which is the external force, as we can see here, is only applied to the nodes number 3. To the node number 2 in the x direction. So kita boleh panggil our force dekat sini ni as our F3 untuk this one. And then this one we can call it F6 equal to negative 25000 pound. Negative to shows that the directions of this force in the downward direction, which is opposite to our positive y-axis. So when we have this, we substitute this information into our matrix. So K3 we have berapa tadi? 21,000 21,000. 5 kita tak ada. Yang ni we have negative 35,000 pound.
Says Q3 to 20,000.
20,000 tadi. Yes, okay, thank you. So this okay. So tengok, this is our system of linear equation sekarang. So saya boleh remove lah yang ni. Yang ni kamu punya constant lah kat sini ni. Constant. Constant which is came from this lah kat sini ni. So now you can see how much work reduced. Instead of kamu nak prepare yang ni, yang very big ni, 8 by 8, nak tulis semua lagi. Now we just cut short the process. We just prepare yang ni je kan. Which is later on, kalau kamu tengok daripada sini ni, if we move to the next slide, kita akan dapat benda yang sama ke ni. Kan, kita dah dapat. Tapi, the way they prepare, dia buat semua benda dulu, then baru dia reduce kan. Which is not very efficient approach lah. Tapi kalau dalam komputer dia akan buat ni semua benda ni. Komputer tak apa kan. Dalam komputer memang dia akan list everything. And then bila dia apply boundary conditions tu, then dia akan reduce lah. Tapi untuk kita punya practice, we can work in slightly different way. Kita straight away tengok kepada boundary condition, and then we come up with the reduce itu yang dipanggil sebagai reduce equation for the system of a linear equation. So untuk plane trusses problem, starting from I think last 3-4 semesters before, we have changed the way the students answer the problem, because sebelum ni the way student jawab problem tu dia macam purely mathematics kan. Kalau matrix tu kamu solve matrix je, then tak tahu nak pakai ke mana apa guna matrix ni. So apa guna cosine yang kamu belajar sebelum ni tu kan, ataupun cos elimination. So we change a bit so that you can understand dekat mana nak gunanya matrix yang kamu belajar tu. And then Gauss elimination yang kamu belajar dekat algebra ke dalam advanced mathematics punya course ke, dekat sini kita nak pakai dia kan. So starting from I think last 3-4 semester before, for the plane trusses, starting from this stage, you have to solve this system of linear equation strictly using Gaussian elimination. Gaussian nak tulis pun susah. Gaussian elimination. Sorry lah, saya punya tulisan buruk sangat ni, pakai mouse je. Gaussian elimination. Alright, so tapi dalam example ni, actually even tu dia pakai Gaussian elimination, dia punya detail solution dia tak diberikan kan. Tapi untuk plane trusses problem, you have to solve using Gaussian elimination, and you have to show in detail the Gaussian elimination process dengan dia punya backward substitution. So dalam Gaussian elimination tu, dia ada part which is we call it as a backward substitution. Itu yang kamu buat dalam first assignment kamu kan. Tapi dalam first assignment tu, kita just bagi metrik dan kamu solvekan. Tapi metrik tu untuk apa pun tak tahu kan. So actually that metric which is making from this system of linear equation generated from the plane trusses problem. Saya tulis kat situ kan, backward substitution. Barulah kamu boleh dapat Q3 sama dengan berapa, Q4 sama dengan berapa, dan Q5 ni Q5 sama dengan 356. Sorry, 356. So once you solve this 356, dan the mark distribution untuk this Gaussian elimination ni very big. Kalau kamu tak buat yang ni, memang kalau jawapan tiba-tiba dapat betul pun, kita bagi kosong je. Sebab macam mana datang numbers ni kat sini kan, kalau tak ada dia punya solution. And then kalau ada solution pun, then we look at the step here. Kadang-kadang kita faham sudah kan, sini tiba-tiba rasa tak betul aku buat, then suddenly jawapan ada yang betul kan, itu pun sama. Alright, that's why I prepare this assignment number 1. Look like very simple, but if you do not practice solving this Gaussian elimination, then you will be struggle during the test. You will struggle during the test. What I can suggest, you can repeat that assignment several times. Mula-mula buat just untuk dapatkan confidence, build your confidence level. Oh, macam ni dia punya method dia. So once you understand the process, then try to challenge the time. Untuk solve Gaussian elimination, how long should you take to solve 3x3 punya equation kan? Nak ambil setengah jam nak solve, lama sangat. Okay. Try to reduce it. Untuk first test, your time is only 1.5 hour. You have 2 questions, and maybe in one question that you have 2 parts. So you have to plan answering your the test or exam properly. Otherwise, you don't have enough of time. Our experience before, baru ni kan banyak isu yang online plagiarism lah apa semua kan. Tapi untuk finite elements tak ada isu langsung. Sebab these solutions, even though if you post in the chat, orang yang dekat chat tu tak sempat nak solve within that time. So that what we aware lah. If you ask someone to solve for you, so they don't have time to solve. Kalau kamu solve sendiri pun, just nice. Kamu siap ya, if you concentrate 100% on solving the problem, just nice kamu siap masa dah tamat. So the time is very tight for the final element. So that's why try to practice it, and you have to repeat practice quite frequently. Repeat soalan satu pun tak apa, build your confidence. You understand, familiar, you feel comfortable with the methods, and then try to beat the time. And then solving using quotient elimination in detail, okay, only apply to this particular topic. Because as I mentioned earlier, we want you to understand that mathematics is applied here. We can apply Gaussian elimination in solving physics problem or engineering problem kan. Engineering problem is a physics problem. Kalau kita belajar sekolah tu, bila kita solve satu-satu benda tu, apa yang kita faham, it's just a number. What is the number for? Kan? So that's what was happened. I have been teaching these finite elements starting from I think 2011, 2012. 2011 saya balik PhD, 2012 saya start mengajar finite elements until now. Then when I at the beginning of my teaching of this finite element, itu yang saya dapati lah. Dulu soalan test satu ada 3 soalan. Soalan pertama tu on the solving matrix. Kalau kamu jumpa soalan-soalan yang lama-lama dulu kan, the first question is solving the matrix using quotient elimination. Itu memang purely mathematics punya problem, which is at one time saya rasa why should we have this problem solved in that way? Sebab dia tak ada link dengan fizik yang kita nak solve kan. Jadi macam kamu solve purely mathematics lah. 1 plus 1 campur 1 jadi 2. So what is this number 2 for? Kan? So then we decide to include, instead of we solve it separately, macam kita buat mathematics sekolah rendah dalam menengah tu. So we include in the problem, then you can feel it much more better lah, the usage of apa yang kamu dah belajar dalam ni. So we improve the way we see out the problems lah. Alright, that's just to let's share with you what was happened in the past few years and how we improve the understanding of the physics and the mathematics among our students lah. And then, okay, once we solve this the Gaussian eliminations in order to obtain the displacement. So bila kita dah solve system of linear equation Q equal to F, then kita akan dapatlah displacement pada 3, 5 dengan 6, which is kalau tengokkan ni very small je for the given load, given structure size and structure the material we use. And then from there, this information will be used in obtaining the structure, the stress within the element. Alright. So for the element number 1, okay, for the element number 1, we need to obtain the. So we go back there. I think I remove all the sketches first. It's look messy now. But if you have any question, tanya tau. Otherwise, the only place. Yes.
Saya nak tanya, macam untuk yang table tu kan, untuk setiap elemen kena ada ke? Sebab saya macam keliru. Contohlah kalau macam elemen 2 tu kan tadi ambil 5, 6, 3 kan.
5,
So,
6, 3.
kena
Yes.
So macam dekat matrix tu nilai dia tu ambil buat daripada table baru atau table yang asal tadi?
Table yang asal.
Table yang asal.
Macam contoh ni kan, table ni, activity ni. Yang ni ke Syafiq?
Yang sebelah, yang table yang sebelah.
Ni, sini.
Okay. Yang daripada nombor 2.
Actually, kamu boleh sambung sini sebenarnya ni. Elemen ni ataupun sambung daripada sini pun boleh. Elemen 1, 2, then ada theta, then ada LE. Buat sekali je, tak perlu buat banyak kali. LE, kamu ada L, ada M sama yang dekat sini lah. Kan? Buat sekali je, jangan buat 2 kali. No waste of your time. And then kita 3, 4, 5, 6 tu depending on the element activity. Dia connected daripada mana ke mana. Kalau daripada 3 ke 2, kita start daripada 3 lah. Kita listkan dia, maksudnya daripada 3 ke 2, kita listkan dia starting from point number 3. Point number 3 kita tengok yang x direction dia dulu adalah 5, 6 and then followed by 3 and 4. Itu ke yang Syafiq nak tahu kan?
Kan kalau matrix kan kita buat 5, 6, 3, 4 kan?
Ya betul.
Lepas tu nilai kita nak substitute dalam matrix tu. Saya keliru sikit. Dekat yang tu. Matrix tu kan ambil 0, 0, 0, 0, 0, 0, 0, 0.
Okey,
saya kurang faham.
Okey, kalau kita tengok yang kita punya matrix kita macam gini. Kan, dalam bentuk variable. Untuk elemen number 2 sebagai contoh, dia punya variable dekat dalam dia ni tak berubah. Dia still main macam gitu je. L square, M square, and LM. Cuma untuk elemen number 2, kita kena tengok elemen number 2 L square kita apa. Okay, this is our element number 2. Ni elemen number 2. Apa dia punya L square dia adalah kosong. M square dia 1. So kalau saya kita tengok yang L square dengan M square dengan LM dia kosong kan. Dan kita cuba tengok kat situ. Kalau saya substitute, kita tengok sini. Untuk elemen number 2, L square saya dah kosong. So kita ada kosong kat sini. Saya padam dulu. Okey. Ni adalah position untuk L square kan. L square untuk elemen number 2 tadi kosong. So kita ada kosong. LM kosong juga. So kita ada kosong. So kita just substitute je. The value into L square LM. Cuma dekat atas dia ni, kita letak dia punya address dia. Kita letak dia punya index dia according to the element connectivity. Itu je.
Okay, faham.
Okay, very good. Ada apa soalan lagi? Kamu kena faham ni. Nanti hanya masa ujian nantilah yang kalau tak tanya sekarang, kamu akan ditanya masa ujian nanti. Masa ujian nanti tak ada orang jawab dah nanti.
Betul. Tak kalau
Saiful.
terang balik yang Syafiq tanya tu, tapi cuba guna yang lain pula, sample ataupun metrik yang lain.
Okay, let's say kita
saya nak nampak
matrik yang mana? Kita
Atau pakai
pakai
0.64 tu ke K3 tu?
Ini K3. Okey, saya sepak dulu. Ni dekat dalam ni sebab dia dah sepak ni. Okey, untuk kita punya elemen nombor 3 ni, let's say lah saya tak tulis dulu dia punya ni, dia punya sorry, dah berubah. Okay, let's say saya abaikan dulu dia punya number kat dekat ni pun boleh. Kita just fill up content dalam ni je dulu. Address atau index dia kita boleh kemudian saja. Tapi kalau kita tak tulis, kita tak tahu elemen mana yang kita nak eliminate kan. Sebab kita nak eliminate di awal-awal. Okay, tak apa, kita just tengok. Untuk elemen nombor 3, kita pergi ke sini semula. Elemen nombor 3. Okey, sebelum tu, yang ni kita tak berubah tau. Yang ni dia still maintain macam ini je. Dia tak akan berubah position. L square akan duduk sini sampai bila-bila. M square akan duduk sini sampai bila-bila. Ini tak akan berubah. Yang hanya berubah dia adalah indeks dia dekat atas dengan dekat tepi tu je. Okey, sebagai contoh, untuk elemen nombor 3. Okey. Saya punya L square 0.4, M square 0.36, LN adalah 0.04 dan 0.36 kan. Saya tak tahu apa sini. So kita tengok untuk kita punya elemen nombor 3. So ini adalah AE over L dekat depan ni. Ini kamu jangan tertinggal ni. Ni E, satu adalah A over L. LE, length of the element number 3. Berapa length of the element number 3? Ini kita punya length of the element number 3. 30 square tambah 40 square. Kita square root kita dapat 50 kan. So this is the length of our length. Kita measure je macam gini. So this is the length of our element number 3. And then itu jangan tertinggal. Okay, now we look at this the contents element by element dalam kita punya matrix. Tadi kita dah tahu yang L square adalah 0.64 kan. Dan dalam matrik kita L square tu duduk kat sini. Dan kita letakkan dia 0.64. And then kita punya M square sebagai contoh adalah 0.36 tadi. Dan kita letak dia dekat position dia dekat sini. 0.36. LM sebagai contoh adalah 0.4 darab 0.36. So kita kali darab kita dapat 0.48. So kita masukkan plug in je dekat sini. Kita plug in je dekat sini according to the value yang kita dah prepare dalam table ni. Kan? So kat sini kita dapat 0.48 lah kat sini. 0.48. Then kamu repeat lah. Tengok. Kita ada S square tapi negatif. So value S square kita 0.64, kita letak dia negatif. Okay. Cuma dalam case kita tadi kita eliminate kan. Kita eliminate dia based on the calculation. Kita eliminate. So yang ni kita tak perlu isi. Kita just isi apa yang tinggal dia. So yang tinggal dalam case kita sekarang ni adalah S square LM M square. Itu je yang kita tinggalkan. So whatever we do ni kita dapat daripada table yang kita prepare tadi tu. Kita plug in je, dia masuk je ke sini. According to the attachments of the L, M dengan M square ni. Okay kan? Ataupun
Faham.
kalau agak kurang faham lagi, boleh cuba tengok yang dekat YouTube. Cuma, saya nak highlight dekat sini, for whatever elemen connectivity yang diberikan ataupun yang kamu decide, kamu punya matrix, local matrix tu mungkin lain. Kan? Mungkin let's say one of you solve problem pada macam-macam saya bagi tahu sebelum ni, mungkin kita beri elemen connectivity, kan? In some problem, kalau kamu pergi buat engineering punya projek, benda ni tak diberi pun, kamu tak tahu pun, kan? Dia tak ada ditulis dekat mana-mana pun. Then we engineer have to decide how our element is connected between each other. So in some cases, dalam practical exam, we even didn't provide you the element connectivity, so you have to decide yourself. So maybe student A dia nak solvekan based on element connectivity 1 to 2, then solve according to this arrangements of the element connectivity dengan K matrix dia start daripada untuk K1 in term of dia punya index dia akan start daripada 1, 2, saya padam sikit, 1, 2, 3, 4, kan, dalam dia punya K matrix dia. Tapi kalau ada student dia nak solvekan, yelah, dia dengan cara dia kata dia pun boleh solve pakai 2 to 1, so still boleh solve juga, tapi the arrangement of kamu punya matrix nanti in term of dia punya index dia akan berlainan lah, kan? Kalau kamu solve daripada 1 ke 2, kamu akan ada susunan 1, 2, 3, 4. Kalau kamu solve daripada 2 ke 1, so dekat sini kamu akan ada ada 3, 4, 1, 2, 3, 4, 1, 2. So susunan dia berbeza, kan? Susunan dia berbeza. Tapi when you assemble the whole matrix, bila kita nak assemble, kita kena susun dia from the smallest numbers lah. From the smallest 1 sampai pada biggest. So bila kita susun dia macam ini, from the smallest to the biggest, whatever element connectivity yang kita pakai actually will give you the same result. Bila sampai di stage ni, kamu pakai 1 ke 2 ke 2 ke 1, bila sampai di stage ni dekat sini ni, bila kamu dah assemble, kamu akan dapat value yang sama. Kalau kawan pakai 1 ke 2, 2 ke 1, dekat sini dia akan sama. Okay. Tapi we have to remember which is for every K elements K matrix yang kita prepare, this matrix should be diagonally symmetry. Okay. Kalau kamu confident yang kamu punya matrix kamu symmetry, kamu boleh further reduce lagi. Kan? Instead of kamu tulis full macam yang slide dekat bawah ni, 3 by 3, actually you can write half of it. Just tulis all the values on this part ni. Yang dekat bawah ni, boleh tulis dia symmetry. So just prepare the diagonal and 1, 2, 3 elements lagi dekat sini. Tapi you have to be very confident lah yang kamu punya pada elemen stage lagi tu, kamu punya semua matrix 1, K1, K2, K3 semua dah symmetry, kan?
Saya
Yes.
kiranya walaupun connectivity kita macam lain dengan kawan kita, so
Yes.
waktu dekat global tu sign pun semua akan jadi sama balik.
Ya, betul. Bila dekat global, dia akan jadi sama. Cuma dekat local stage tu, dia akan lain lah sebab angle dia akan lain. The length angle akan lain. Sebagai contoh saya tunjuk yang elemen nombor 2 ni kan. Sorry. Elemen nombor 2, kalau kita punya connectivity from 2 to 3, so kita draw reference line kita dekat sini, kita drawkan kita punya angle, then kita project kita punya angle tu from the reference line sampai dia jumpa elemen yang bertemu. So kita punya angle kat sini adalah 90 degree kan, 90 degree. Tapi kalau the element connectivity is from 3 to 2, so kita kena draw kita punya reference line pada node number 3 ni, and then we project kita punya angle tu in this direction sampai dia jumpa elemen number 2. So now kita ada 90 degree dan dekat sini kita ada 270 degrees. Kalau kita tengok cos and sin punya, saya ambil masa seminit 2 lagi. Kalau kita tengok kita punya sin dengan sin wave, so kat sini positif 1, dekat bawahnya adalah negatif 1, and then saya ambil another which is the sine wave. Okay, dekat mana sini 90 kan, sini 90.90. Sorry, saya pakai yang lain. Ini adalah point 0 degree 90, 180, actually macam ni. And then dekat sini 270 dengan 360 ni kita punya angle lah, letak. 90 dengan 270 ni dia macam opposite je. Kalau kita tengok angle dia ni, kalau kita goes in this anti-clockwise, kita ada dapat 270. And then kalau kita pergi ke arah sini, it's like we have negative 90 degrees lah. So, untuk mengelak kekeliruan, saya recommend kamu follow one direction je. Okay, instead of kita just follow one direction which is in anti-clockwise. Just in anti-clockwise. Kalau, let's say ni, kalau elemen number 4, from 4 to 3, kita boleh ambil dia kosong ataupun 360. So biasanya kita ambil kosong je, 0 and 360 sama je kan. Kalau kita ambil this sine wave kosong degree, value dia kosong juga. 360 nilai dia pun kosong juga, sama dengan cos wave kosong, nilai dia 1. 360 nilai dia 1 juga. So instead ambil 360, kita boleh ambil kosong je sebenarnya. Okay, nanti kita akan ada assignment on this similar example, which is kamu dah ada solution dalam slide ini, dan saya recommend kamu repeat menggunakan approach yang kita discuss tadi kan, di simplified versions lah, dengan elemen connectivity yang diberikan ni. And you try to build your confidence, you try repeat one by one process kan. And then dalam assignment nanti you will be given the element connectivity yang berlainan daripada yang ni. Then try to and then you have to compare dengan result yang ada dalam slide ni. Ini adalah untuk proses untuk build your confidence level lah kan. So next time kalau kamu jumpa benda macam ni, so kamu tak kisah alah ini aktiviti lain pun dah tahu dah kan. Dekat local stage mungkin lain, tapi dah sampai global stage semua sama je nanti kan. Tapi nak sampai to that level, you have to prove yourself first. Betul ke kan. Kalau kita dah prove, kita dah jumpa benda tu betul, then kita dah confident. Kita nak solve sesuatu benda pun kita confident. Kalau kita tak proof, kita tengok tapi kita tak cuba proofkan sendiri. So our confidence still not confident level tu not 100% kan. Alright, then yang seterusnya tu nanti you all boleh tengok je lah dekat ada sikit je lagi untuk elemen aktiviti dengan support tu nanti boleh tengok dekat ni lah daripada YouTube tu ada sikit lagi. So tapi kalau tak faham kita boleh sekali besok lah sikit je ni. Alright, I think saya stop kita punya meeting dekat sini. Then please give me 2-3 minutes so that I can prepare the QR code for you to record your attendance. Do we have this? Sekejap ya. Saya rasa okay, ada ingat dia down lagi ni. Kita terus bila malam tak apa. And then I share this with all of you. So okay, I share with you the QR code. So what you have is please submit your QR code as soon as possible. So once you submit your QR code, then you can leave our meeting lah. Thank you very much for your